right, so I just wanted to go over really quickly the last thing that you might encounter on the quiz coming up. And it's related to Lewis structures. It goes with all the things we've been talking about in terms of shapes, etc. And that is polyatomic ions. Remember, polyatomic ions from the last unit are groups of atoms that together overall create a charged particle. So the group of atoms as a whole has a charge and acts like an ion, like a sodium ion or a chloride ion, but it's a group of atoms that does that. We can draw Lewis structures for these because they are atoms that are bonded together like a molecule. It's just that the number of electrons is different from what it normally is. And so you end up with a group of atoms that has a charge. So I want to quickly go over a couple of examples because you will see a couple of these in some of the things we're working on. And there's really only one difference in the process in terms of how we figure the numbers for the NaSl. And then there's just a little bit of kind of a formatting thing that we do at the end to indicate that this is a polyatomic ion and not just a molecule. So first, we can do NH4, positive 1. This is the only positive polyatomic ion. So the only time you'll have to deal with the positive charge. All the other ones that you're going to see are negative. So I wanted to show you this one first because it's the only one of its kind. And so if you do see this one, it'll be done the exact same way I'm about to do it. So we'll start with the NaSl. I will place the atoms roughly, right? 1 nitrogen, 4 hydrogens. And then we'll do our N. So for N, we don't do anything differently than we would for a regular molecule. Hydrogen each need 2, and nitrogen needs 8. Okay, so if we add all that up, it's 16 needed. Okay. And then we do the A, which is looking at how many valence electrons there are that are available. Hydrogen has 1 valence electron each. Right, so 1, 2, 3, 4. Nitrogen has 5. So that's a total of 9. Now remember, I said if you get odd numbers in this process, there's a problem. 9 is obviously an odd number. But what we have to take into account here is that this group of atoms has a charge of +1. And remember, the plus charge, positive charge, means that there are not as many electrons as normal. +1 means 1 electron is missing from this equation, literally. So when we figure the available electrons, we have to adjust that number based on the charge. So it's 9 minus the 1. So you do the opposite of whatever the charge is. It's a plus charge, so I'm going to subtract 1, which means I really have 8 available. Okay, so that is the only step in this process that's different because of the charge. It has to do with how many electrons there actually are. And in this case, it's 1 less than normal. With negative ions, it'll be more than normal, and we factor that in only in the A step in the process. Everything else is exactly the same. So from here, we have 16 needed, 8 available, which means we need to share 8. And if we have 8 and share 8, we're going to have none left over. So let's go through and do that. Okay, so if we're sharing 8 electrons, that means 4 bonds. 1 bond for each hydrogen from the nitrogen. Now, if you look, each hydrogen has 1 bond, which means 2 electrons, which is what it needs. The nitrogen has 4 bonds, which is 8 electrons, which is what it needs. So just like with a molecule, this polyatomic ion has created a situation where the bonds make each atom a complete octet, or in the case of hydrogen, it's 2, not 8, but it's complete outer shell. So the last piece, the only other thing that we do differently, because this has a charge, we put the entire drawing in a pair of square brackets and then we put the charge outside the brackets like that. And that's really just to kind of show anyone looking at it that, because if you looked at this normally, you'd say, wow, there's an electron missing. The brackets with the positive charge kind of says, yeah, I know that. That's because this is a positively charged ion, and it's deliberate that that electron is missing. So that's the difference there. So the difference is we change the number for A. Everything else we do the same. At the end, we put the whole drawing in brackets with the charge on the outside. Let's look at one more, an example of a negative one. Phosphate, PO4 with a charge of -3. Set up our NaSl. Okay, we set up our atoms, phosphorus and 4 oxygens. All right, need. There's no hydrogens here. So what we do is we just look at all the atoms and say they all need 8. 1, 2, 3, 4, 5 total. 5 times 8 is 40. So we need 40 electrons. Oxygen normally has 6 valence electrons. Phosphorus normally has 5. All right. So if I add all that up, it's 24 plus 5, which is 29. Again, odd number, 29. That's how many I would normally have. But we have a charge here, which means that the number of electrons is not the normal number. The fact that it's negative means there's more electrons than usual. The fact that it's -3 means that there's 3 more than usual. So again, do the opposite of the charge. The charge is negative, so I'm going to add 3 electrons. So what I really have available here is 32. Now it's a nice even number. I can go from there. Take the n, 40 minus the 32, means I need to share 8. Sharing 8 means make 4 bonds, which is good because I have 4 atoms that I need to bond to. So there's 1, 2, 3, 4 bonds, 8 electrons being shared. Okay, there's my S. And then the leftovers, 32 minus 8 is 24. So I need 24 dots or lone pair electrons. Look at the center atom first. The phosphorus has 4 bonds, already 8 electrons. It doesn't need anymore. So that means the oxygens are the ones that are going to get these dots. Always start in the middle and then work your way out. And if you look at these oxygens, all of them right now have a bond and that's it. So they only have 2 electrons. They each need 6 more. Well, conveniently, if I put 6 electrons 4 times, that gives me the 24 electrons that I just said I need to share. And it gives each of those oxygens the 8 electrons that they want. The phosphorus has 8 electrons already because of the 4 bonds. And then the last piece is to put the whole big thing in brackets and put the -3 on the outside to indicate, yes, there are more electrons there than normal. And that was on purpose because this is a polyatomic ion. And if you wanted to talk about the shape of this molecule, it's 4 bond pairs, no lone pairs. That's a tetrahedral shape. And that was actually the first, I didn't do that on the ammonium, tetrahedral. And if we wanted to talk about the polarity of a polyatomic ion, there's all the terminal atoms are the same. There's no lone pairs on the center atom, so this would be a non-polar group. And that would be true also of this one. Again, this 4 bonds, no lone pairs, tetrahedral. And since all the terminal atoms are the same, no lone pairs on the center atom, that would also be nonpolar as a group. In general, if you have a tetrahedral, that means there's no lone pairs. So for tetrahedral shapes, if the terminal atoms are the same, it's not going to be polar no matter what. So nonpolar, just in case, right? And go back to this one, and we'll say the same thing. Nonpolar. Okay, so again, 2 things that you do differently for polyatomic ions versus molecules. One, you adjust the number for A in NaSl. and you do the opposite of the charge. So if it's a positive charge, you subtract electrons from the A. If it's a negative charge, you add electrons to the A. Go through the rest of the process exactly like you would, and at the end you put brackets around the whole thing and put the charge on the outside of the brackets, and that's it. Then you can come up with the shape and the polarity using the same methods that we do for molecules. All right, so I just wanted to show you that because you're going to be coming across those in some of the worksheets coming up. And that's it. Other than that, it's just practicing your geometries, your Lewis structures, identifying the shapes and the polarities. All right, there you go.